Okay, welcome to the challenges video. I'm going to write out these challenges with a number of steps that'll make it easier for you to complete this task. If you really want to have a go at something difficult, at the start of each challenge you can pause the video and have a go at it yourself. But even if you do follow through with my steps, you're still learning how to reason your way through things in the same way that all mathematicians do. Okay, so let's get straight into the first challenge, which is proving Pythagoras number 1. So let's start off by pasting in the arrangement of triangles that I did before. And just for ease of reading, let me change this A, B and C into white. And recall that both the diagrams on the left and right are just different arrangements of the same 4 triangles. Okay, and each one of those triangles is the same as a triangle on the left there. Okay, so to do this proof, step 1 is drawing both arrangements of triangles, including the containing box. And in step 2, you're going to use the lengths given in the triangle to mark in the side lengths of the diagram. So that's every side length, okay? Then if I mark in these angles alpha and beta on the original triangle, I want you to mark them in on the left diagram and then use them to figure out the angle X. If you get stuck here, I can help, so contact me. That could be by email, through the OneNote, through Teams, or in the comment section. So hopefully you did well in our geometric reasoning block, because in step 4 you're going to use what we know about quadrilaterals, plus what we know about that side length, plus the angle we found in step 3 to show why J is a square and what its area is. So let me mark in J on the diagram. And in the next step, we're going to use these areas, K and L. Let's talk about step 5, where I want you to use the side lengths and the angles in the diagram on the right to show that K and L are squares and what their areas are. And let's just move up to these diagrams so I can name them. I'm going to name the diagram on the left A and the diagram on the right B. And in step 6, I want you to use the side lengths to figure out the area of the diagram on the left A and the containing box on the right B. Step 7, I want you to use the area of A and B plus the area of the triangles to show that J equals K plus L. And then in step 8, complete your proof by stating how all of these facts that you have reasoned show that Pythagoras' theorem is true for all right-angled triangles. And you may want some hints from GeoGebra, so you can use this applet here. Okay, so that should help you complete that proof. Okay, let's move on to the next challenge, which is challenge 2, proving Pythagoras' theorem, number 2. And let me paste in the diagrams for James Garfield's proof of Pythagoras' theorem. The diagram on the right is a trapezium that's created by 2 copies of the same right-angled triangle on the left. And I know we're going to learn this in our next lesson, so it's worth noting for a trapezium with these sides M, P and N, the area is P times M plus N divided by 2, where M and N are the 2 odd shapes and P is the other flat shape. Okay, so step 1 will be to mark in the side lengths of the trapezium based on the lengths of the right-angled triangle. Then step 2, you're going to figure out the area of this trapezium based on these lengths. And then step 3, figure out the area of the 2 pink triangles. And then in step 4, I want you to figure out the area of the green triangle by considering it as the area of the trapezium minus the area of the 2 pink triangles. And so let's mark in the angles alpha and beta on the original triangle. So in step 5, you can mark the angles alpha and beta in the trapezium and show that the green angled triangle is a right angled triangle, i.e. y is equal to 90. And let's mark that y in on the picture. Then in step 6, you're going to use y and the side lengths to figure out the area of the green triangle. Then finally, step 7, you use your answers to step 6 and step 4 to show that c squared has to equal a squared plus b squared, and hence you've proved Pythagoras' theorem. Twice. Once again, you may wish to use my GeoGebra applet for hints. Alright, good luck with that one, and I'll see you in the last challenge. Okay, and finally let's get on to the last challenge. This is challenge number 3, where we'll be estimating pi. Now this is a method that Archimedes used to estimate pi over 2,000 years ago. I introduced it to you in the last lesson. But make sure you stick exact solutions in each step. This will allow you to find a pattern and a formula. And by this I mean leave your answers in square root form. Okay, I'm going to paste in a circle and some equilateral triangles where all the edges of the triangle are 1. This means we have a radius of 1. And because the circumference of a circle is 2 pi r, the length of the semicircle is pi r. And we'll mark in that semicircle with this line, which I'll call L. With a radius of 1, that means that L is equal to pi. And our first estimate for pi is P1, which I'll mark in on the graph. Now because P1 is 3 lines of length 1, that means that P1 is equal to 3. It's not such a good estimate, but it's not that bad either. Now let me copy that triangle and magnify it. Let me draw a line that goes from the center of the circle to the edge of the circle. So because we're going from the center to the edge, this pink line is another radius. So that means that the pink line must be of length 1. And we know that the green lines are 1, so that means that this line here is 1, and this pink line's cut the green line in the edge in half, so these lines here are both 1/2 long. Now I'm going to draw 2 purple lines. There will be 6 of these purple lines around the semicircle, because we have 2 for each of the 3 triangles. And let's call the length of all these new purple lines B1. So we can call our new estimate for pi P2, and that's equal to 6 times B1. Alright, let's move on to part 1. And this is where you're going to start answering your questions. But first, let me paste in a diagram of the new triangles we've created by drawing that pink line. Now I've left the colours the same, so you should recognise it. And we can see the lengths that we already know are marked in. But there's 2 other lines here that are very important, okay? And so I'm going to mark this one here as x1 and this one here as y1. These numbers or algebraic terms are just to represent the length of that line. Okay, so let's get on to your questions. In part A, I want you to use Pythagoras' theorem to figure out the length of x1 and leave that in exact form. Then in part B, I want you to use Pythagoras' theorem and the fact that x1 plus y1 has to equal 1. And that can also be expressed as y1 is equal to 1 minus x1. And this should allow you to figure out b1. And then in part C, give us your new estimate for pi, which will be equal to p2, which is 6 times b1. Alright, now let's move on to part 2. And for this I'll need to copy a part of the triangle from part 1, but with some of the outside of the circle drawn in. I'm going to delete this line here because we don't need it anymore. And now we're left with an isosceles triangle that has sides 1, 1 and B1. And I've added L back in there just to give some perspective on where the circle is. Now if I draw another blue line up the middle of this one, this line has length 1 as well. And now I'm going to draw in 2 new purple lines. And these purple lines will be our new estimate of pi. But I'm going to also delete L, which should make it clearer that we've created some new right angle triangles. Now I'm marking the length of these lines. First let's delete B1. We've split this line in half and I'll change its colour to orange. So now this orange line is 2 lengths of B1 divided by 2. And we'll call these new lines that are part of the estimation of pi as B2. And now we'll break up this blue line exactly like we did in the last part, and we're going to call it x1 and y1. So this part here is x1 and this part here is y1. So okay, for this part of the challenge, part A is using Pythagoras' theorem to figure out the length of x. Leave your answer in exact form. Now in part B, considering that x2 plus y2 equals 1, use Pythagoras' theorem to figure out the length of b2. And this is a post-edit edit. I've noticed I've just made a mistake here. On the diagram where I've written x1, that should be x2. And where I wrote y1, can you guess that that should also be y2? Okay, so b should make a lot more sense now, okay? x1 and y1 add together to make a length of 1. And using Pythagoras' theorem, you should be able to figure out b2 after you've figured out what x1 is. Alright, back to the video. And then lastly, C for part 2 is considering that P3 is going to equal 12 times B2, what is our new estimate for pi? And now let's move on to part 3. So in part 3, my question for you is, can you figure out the pattern and maybe some more steps to improve the accuracy of this estimation of pi? And here is that GeoGebra applet I used in the last class that could potentially help you. I'll make sure I paste a link to that in the video description as well, but obviously it's here on the OneNote page. And finally, let's look at part 4. And A in part 4 is, can you create a spreadsheet to continue making better estimations? I realize a lot of you won't have a lot of experience with spreadsheets, so if you want, I'm definitely open to helping you with this. And finally, how many steps will you need to make to get the exact answer to pi? Okay, so that's the end of the challenges. I would really like everybody to have a go at that. You can do this in your own personal OneNote pages, or you can work in the collaboration space, or you could even make comments here in the video. Anyhow, have a great day and I'll see you in our next lesson. See ya.